Hello everyone. So today we will be talking about classical mechanics. Not we. It's just me. I will be talking. You listen. Uh, so basically, classical mechanics like when something which most of the stuff which you can see from your eyes comes in classical mechanics. Like you can directly see it from your eyes. Um, or at least through a telescope. So a ball, throwing a ball up, it comes down. Classical mechanics. Car going in a certain direction, and then um, when it stops, it means some force was applied in opposite direction. So that's why it stopped, and I don't know what not. Too many things. So classical mechanics. So today in classical mechanics, more specifically, I want to talk about this thing called symmetry. Symmetry. This thing actually fascinates me. So I don't know. Uh, I feel good when I talk about this topic, symmetry. Like, what does symmetry mean? Like one of the example I will give. So, uh, what I mean by symmetry, basically, in class, like when I'm talking here, what I mean by symmetry is, imagine you have a square, and simply tilting it a little will so let me use this. If I tilt it a little, you will easily tell that I have tilted it. But if I tilt it at a specific angle, let's say, and that angle is 90-degree, or maybe I'm wrong. Is it okay? I think it is 90-degree. If I tilt it perfectly 90-degree, you will get a square back, and you will never be able to tell if I tilted it or not. Another example is a heart. Let's say a heart symbol, a heart cookie, a biscuit. So if I flip it this way, it looks again like this, and you will not be able to tell if I had actually flipped it or not. So that's uh, that's what it means, symmetry. So if this is clear, I think I can go more. uh, you will never be able to tell if I flip it or not. So there are a lot of things. Uh, so how am I flipping this? So basically, I am flipping this. This is a kind of a line, like things in this direction. On this side of the line and things on this side of line look exactly the same. That's what it means to have symmetry. Another example, I can go on and on, but there are two kinds of symmetries basically. Like for example, let me give another example. Let me take a circle. So let me take a circle. So I need a circle. So if I have a circle, the circle is even better, because look, for a heart I have to I have for this heart I have to give a very specific kind of tilting, like I have to rotate it to a very specific degree, and here it happens to be 180 degrees. For the square I have to go 90, like only if I orient it in a specific shape it will give me back my old shape. You will not be able to tell if I reoriented it or not. But for a circle there is some speciality. If I Even if I rotate it by, let's say, 0.00001 degrees about the center, you will not be able to tell if I rotated it or not. I don't know where the center is, maybe somewhere here. So this is something which circle can do, and the other none of these shapes can do. uh, so I call this a continuous symmetry. Basically, even a tiny minute, uh, doesn't matter, like doesn't matter how tiny or how big, uh, if I orient it, it still stays the same. Another example of a continuous symmetry is a football. So like if you have a football, a sphere basically. Okay, sphere is a circle. Let me give another example. You might be aware of a rugby ball. It looks something like this. So let me show a rugby ball. So this is how a rugby ball looks, and so this rugby ball, if I uh, rotate this uh, in a particular direction, doesn't matter how small or big, you will never be able to tell uh, how I rotated it. This is a special thing about this shape. Like for example, uh, let me take that here. If I take this rugby ball, uh, if I take this rugby ball, if I rotate it about this line, then of course you will be able to tell that I have rotated it. But if I had rotated it about this line, you would have never been able to tell me how I rotated it. Okay, provided there are no designs, none of these designs here, stitches, or else you will tell. Imagine no labeling is there. So this is a continuous symmetry, and I am mostly interested in continuous symmetry right now. Discrete, I won't talk about it much. Basically, I mean continuous symmetry. Symmetry is where doesn't matter how small or doesn't matter how small or big uh, translations. Yeah, I would like to say translation. So this rotation was a translation in angle. This is also translation in angle. Doesn't matter how small or big translations you do. Every translation, every value of translation will give you the exact same configuration as you had before. So that's a continuous symmetry. So why does this matter in classical mechanics is so if you have a planet, okay, so if you have a planet, let's say this is our earth, and so because an earth has this gravity which pulls everything towards it at the center, and so think about it, like if even if I slightly rotate it about the center, it doesn't matter, everything still stays the same. So there is a continuous symmetry here, and continuous symmetries are very important in classical physics, and they are amazing for they really amaze me actually, because every time you have a continuous symmetry about in some translation, I don't know what the translation is, it can be angle, it can be time, it can be anything, you get some kind of how should I say, fixed number. This number turns out to be very special. uh, what do I mean by fixed number? Like these fixed numbers in physics mean energy, momentum. You must have heard like momentum is always conserve energy, conserve blah blah blah, and angular momentum, mass. These are fixed numbers. Charge, all these things. Um, some of these are fixed only in certain point of view. If you change the point of view, they may not be fixed, but um, not some of them, maybe all of them, but overall fixed. I mean, by fixed, I mean just if two people see it at the same point of view, uh, they must see it is not changing. That is what I mean by fixed. So, if you have a symmetry in some translation, then you have a you get a fixed number because of the translation symmetry, and that fixed number we call conserved quantity. Well, it turns out that since in gravity, if you have this symmetry about rotation, right? It doesn't matter in what angle you how much magnitude you rotate, you still you will never be able to tell if I actually rotated it or not unless I mention it to you. So because of this angle invariance, okay, let me not use that word, symmetry, like if I do translation in this angle, I am not getting any change. It turns out that there is a quantity called angular momentum, which is a constant of motion because of this symmetry. And all this uh, uh, was perfect, like all this was rigorously proved by a mathematician called Emin Noether. I'm just telling like a drunk person, a layman guy, but it was very rigorously, strongly proved by Emin Noether using things like Lie algebra, mostly Lie algebra, uh, but this mathematician also was very good in differential geometry, and one of the most influential figures um, at that time. So yeah, this thing is a really amazing uh, thing, amazing concept, that the symmetry, if you have a symmetry you will get some conserved quantity, and also the opposite is should be true, that if you are getting some conserved quantity, there must be some translation which is not changing anything. What translation that is a different question. So how will we show this in numbers, like quantitatively, like writing by the math. So basically we do it by using this thing called Lagrangian, and there is, because of Lagrangian, there is this thing called action, and because of this action, how should I say, so let's say you are in some system, it can be anything. Let's say this cube is your universe, everything, you don't care what is happening outside this cube, only whatever is inside this cube matters to you, and you know everything, whatever there is in this cube, and so this is not a infinite cube, this is a small cube, this is like some cube which you know all the dimensions of. This is a well known cube, you just know everything inside this cube, and you basically you found out force everywhere, how much force is everywhere, you know what is the time everywhere, you know length, everything you know in what is in this cube. So now you want to find out, okay, I know everything at some instant of time, I know everything, whatever is happening in this cube I know. Now your question is, as the time passes, uh, what will happen in this cube? As time passes, whatever numbers you had, like whatever measurements you had done, what will happen to those measurements? What will increase, what will decrease, what will happen as time passes, you want to find out. So to do that you have to write Lagrangian. So basically everything you know in this uh, like find all the energies in this cube, every energy will either be written as kinetic energy or potential energy. Find that out, whatever it is, and you set the Lagrangian, kinetic energy minus potential energy. So at every point, this is you have, so this is a function of space. So at every point, whatever the kinetic and potential energy there was, you just wrote it down, and this can also be function of time, uh, but let's not worry about that for now. Let's just say no time, just you just know everywhere. And what you have to do is, uh, so you you could just consider 2 points, and also let me be more specific, you are only interested um, in what will happen to a certain particle, a certain object, a small object. Let's say this is that object, you know that at time t, at some time it was here, now you have to find out where it will go after some time, where. So what you have to do is, because of this Lagrangian, uh, so basically you have to consider every single direction it can go from here. So it can go like this, like this, like this, I don't know, there are so many places it can go, this one point. Now what you have to do is, this you have to find out mass of this thing, and initially how fast it was it at rest, was it moving, if it was moving, how fast it was moving, just find everything out about it, and uh, write it, write its kinetic energy and potential energy. Of course you don't know what it will be at every point, but you can write its expression. So it will be something like half mv square, this will be kinetic energy minus whatever the potential is everywhere, because you know everything about the box, so you know what is the potential everywhere. So it will be something, I don't know what it will be, it will be something which you have to find out, you have to experiment, I don't know what you will do, you have to find out. This is not our thing, this is given, this should be calculated, doing physically you have to find out. So now uh, so now uh, once I know this, what I have to do is, I don't know where it is going, but I will assume that it is going some point or not, I don't, because the thing is, I don't know where it is going, but I know for sure after some time, it can only be at some point. It can't be everywhere. The moment from the moment it starts from to the moment it ends, it will only occupy one place at a time. Like for example, if I have a ball, it was here. Okay, initially it was here, and after some time passed, this ball is here now. Okay, um, I didn't knew where it will go, but after some time I do know that it can only be at one place, at one particular place. It is not like it will be at 30 different places at the same time. No, this is not allowed. Wherever it went, it will it will be there at that one place, because this is what our ideas are. This is what we think should happen. A ball can't just magically become 10 balls and be at 10 different places. One ball will only be at one place. We don't know where it is, but it is somewhere. But this is, well, quantum mechanics says no. Quantum if you there is another language of physics, I mean another domain of physics, a realm of physics, quantum physics. There everything is uh, at everywhere at the same time. That is a crazy bizarre idea. We will not go here. We will um, just consider uh, an object can only be at one place at a time. So I don't know where it is. Let's say initially it was at R naught, at some place, and after some time it is here, R1. So what you have to do is, at every instant you have to calculate, like it will have some path. I don't know what trajectory it will follow, but if I find out the trajectory, I don't know what it is, but every instant if I uh, find out its Lagrangian in the trajectory, multiply it by the time it spent in that region. Like let's say from the particle, like your object went from here to here, your small object, and let's say it was here. Then from, so at some point it will be here and it will go here, right? From here to here, it spent some time, some interval of time, and let's say throughout this place it had the same on average Lagrangian, some I don't know, at some whatever the time was and the place it is. So so you have to find everywhere what, so at every point you have to find how much the Lagrangian was and multiply it by the time it spent there and just add them all up. Basically you have to do this, add all of them up, and when you do it continuous, it something looks like this. From, so basically initially it was here, you know initially where it was, but you don't know where it will go. We will leave it for later, but basically uh, once you do that, so this will be your, this is called action. So every path, like your particle started from here, right? So every single trajectory it will follow will have its own action value, right? You have an initial point, you have an end point, and between this initial point and an end point you have trajectories, and those trajectories will have their action, and every trajectory will have its, every trajectory will have only one action. No trajectory can have it's like saying uh, how should I say, uh, a 5 kg apple. Oh no, no, I mean a 5 kg watermelon is 5 kg, but as well as 6 kg. It can't happen. Some, so one thing can only have one quantity. So whatever the trajectory is, it will be one, and the claim is, so basically I don't have I'm really not sure why and how exactly, but the idea is, if whatever this ball or this particle wherever it will go, the actual place it will go. I don't know where it will go, but there is some place it will go for sure. This actual place it will go among all these possibilities. This place, uh, this action for this real trajectory will be the least compared to all these other trajectories. Some people say it can also be maximum, and yeah, it may be, but right now we will only focus, let's say that it is the least one. Okay, so this will be the least for all this other, compared to all these other trajectories. So we have to make this the minimum, and whichever trajectory will make this value minimum will be the action of our actual particle, I mean our actual trajectory, the actual path the thing will follow once you leave it there initially with some speed. And it turns out that if this thing has to be minimum, this L, here, and whatever is inside this L, R, and also there will be speed, velocities, should follow this equation. So this is the speed. Uh, so this is what it is. So it should follow this, and this if your L satisfies this means uh, this means that inside this L, the x's and x dots and time and whatever which follow the trajectory will be the trajectory with the least action, and that least action means the actual path. So that is how it is. And so now what we do is uh, so okay, all this is good. So why did I talk about all this? So basically, in symmetry, this thing called symmetry, the problem is, okay, your particle will follow some path. I don't know what it will go from here to here, and this has the minimum action compared to all the other ways it could have gone. And so basically it will start from sometime it was somewhere, and it goes to some other place at some other time, and you have this. So the idea is, if I so let me make it more simple. Just T1 to T2, the moment you know T1 and T2, the position should also be determined. This is what classical mechanics says. So if I have this, if I know the action between 2 points, the idea is, if I do some kind of translation about some coordinate, like by imagine this is your space. No need for space. So this is your cube, right? Imagine I rotated this cube, or maybe I took this cube, what things inside this cube, I just slightly shifted them towards the right, or I am making this cube move, or I can do so many things, right? uh, but basically there should be some kind of movement, some kind of translation in some coordinate like space or time or angle, mass, energy, I don't care, some kind of translation, some kind of change, small change. Yeah, small is important, but right now let's keep small. So if I keep that small change, if this action is still the same, I will say that I have a symmetry about that change I did, about that coordinate. And we actually become a little more layman, and we say we don't even need it to be exactly same. If it is almost same, let's say this was my action after the change. If it is almost same, then also it is fine. What I mean by almost is how should I say? So let's say this is your initially this was your space, but not so this is your space, but now you will do a translation on this space. Okay, and similarly you will do a translation on time. And one more claim is any kind of translation, any kind of change I can represent in terms of space and time, anything, because every motion, every movement you can imagine can easily be represented in terms of space and time. So space and time are my building blocks for any kind of dynamics I want to show. Yeah, the mass will always be there, but right now I will just neglect it. I'm just talking kinematics, the movements. So now uh, so what I mean is, let's say there is some kind of parameter called epsilon, and what this epsilon does is when the parameter is 0, your translation, whichever translation you did, an initial, like your coordinate hasn't been translated. This was initially small x, and it's uh, even after translation it is small x. But if i if i change, like increase this epsilon slightly, then what happens is this x slightly changes. It becomes from x to small x to x. And how we write this is something like this. So basically what we do is this x becomes some other coordinate, and this other coordinate is this, and we write something like this. uh, this is just some fancy math. Don't worry about all this. So now as you can see, when the epsilon, this small thing, when this is 0, all of this just vanish, and you are left with your initial coordinate. So yeah, so and the idea is, and the idea, what should I the idea, if I say, let's say there are two actions, right? Let's say this, my initial action is capital A, and then after doing some kind of translation, the other action is A dash. If I take the difference between these actions, so basically the difference between actions will be A minus A dash, then this will be if this gives some countable value, some big value, finite value, like let's say 100 or 10, 20, something like that, then I can't say there is any kind of symmetry. Uh, I The translations weren't useful for me. Maybe they will be useful for some other thing, but they didn't give me another symmetry, some other symmetry. But if this was, let's say, uh, a multiple of epsilon, like some number was there, but I got an epsilon. Uh, so even then we say that no, there is no symmetry. Even then we are not satisfied. But if it was, let's say, a multiple of epsilon square, or an epsilon cube, or an epsilon 4, and so on, we say that okay, fine, delta A is approximately 0, because we are, remember that epsilon we are taking as a very very small number, let's say 0.00001. So if there is no epsilon at all, which will correspond to epsilon power 0, this is equal to 1. This is a 1 is a good number, I mean 1 is a decent number, and it will be multiplied to something else, so we can't neglect it. Epsilon 1, so this will give me So this epsilon power 1 will give me uh, some epsilon multiplied by some other number. So 0.00000001 multiplied by something else. Well, you may argue that even this is small, but the thing is, whatever epsilon is, epsilon square will be even smaller. Epsilon cube will be even smaller. And the thing is, if you can see a little graphs, uh, so epsilon I will just write it t. So okay, how should I say? So let's say this is your epsilon graph, this is your epsilon square, this is your epsilon cube, epsilon 4. So come very close to 0 and you can see that this thing, this uh, okay, let me uh-huh. Okay, yeah, when you come very close to 0, the problem is, look, this x, this epsilon is like very stubborn. It looks as if it's not changed at all before also. Like, it doesn't matter how close you come to 0, it is always in this one alignment. But look at the other values, the other, even epsilon square is like, the more you closer you go to 0, it the more it just becomes flatter and flatter and flatter and flatter. So what I mean is, so this is something called a linear term. These are not linear, these are higher orders, non-linear terms. There is something beautiful, special about linear things never fall or they never rise. They just stay the way they are. They are just too stiff. Linear things are very stiff. Doesn't matter how much you zoom in or zoom out, they just appear the same. But just increase one order, just instead of linear just increase square, everything goes down. Nothing is linear anymore. I mean, nothing is stiff anymore. Even this, look, this also goes very, you can see the difference. So I can't, so what physics people says, we can't ignore the linear term, but we will ignore every single thing else which is there. Linear has supremacy. Linear cannot be ignored, but non-linear things will be ignored for small values. So I say that uh, uh, the change in my action, if it is even the sum of this is fine, epsilon square plus epsilon cube epsilon 4, even this is fine. But if this is epsilon square or greater, the difference, then I will say it's okay, there is some kind of symmetry. So that's the idea. No, this is not even idea, this is like some kind of uh, how should I say, convenience we came up with. And it's not like it's just something we pulled out. We did not we I did nothing. Those mathematicians and physicists uh, came up with this after a lot of thoughts. And so let's say you have a Lagrangian in your box, in your cube, and after translation this became L dash. So what I mean is, let's say you calculated your action, it was t1 to t2 LDT. But after the translation, after the time and space translation, your action will be something like this. T1 became T1 dash, T2 became T2 dash, L became L dash, and DT became DT dash. And the difference between this should give you order of epsilon square or more. Only then I will say there is some kind of symmetry. So how will I do that? So what we do is we take even a bigger approximation. So first of all, let me write this thing in terms of the old coordinates. So how I can do this is, if you notice, I can write it like okay, you can't notice, I am just talking in the air. I mean, nothing I say probably makes sense for you, but I will try my best. So I will write it like this. So this thing is written now in terms of the old t's and x's, the old numerical values you had without any translations. So, so our another claim we made is if this thing is of order epsilon square or more, then whatever translation you did will be like a symmetry. So how we calculated this? So how we calculated this was so L dash. What will be L dash? So Lagrangian will be uh, so you have coordinates. It will be a function of coordinates, function of speeds of the coordinates and time, right? But now the L dash will be, you will have the same whatever you will do with your coordinates, do it. The rules of the old Lagrangian are still the same here, but now with that coordinate you have to do a translation with uh, let's say every coordinate is getting translated, slightly translated by this, and the other coordinate is slightly getting translated by this. Yeah, like whatever this is, just differentiate it. So like this, but remember the time here is t dash in this space and here it is t. Yeah, but and so finally even the time you just translated a little, and so we do a little more math in this. So this will be written as the old Lagrangian plus del L by del coordinate and multiplied by this small change plus also let's mention the time one. This we will do later because it is actually the more, it takes a more thought.